So, welcome to the nth meeting of the Microcontroller group. Any new? We've got one new face here, Sam. Would you like to tell the group just a little bit about yourself into this microphone? Going to embarrass. The first thing we do, we always embarrass somebody when they first turn up. That's just kind of part of the deal. Yeah. But you get a free cup of tea.
Well, I guess I just do this kind of stuff. I work full-time in electronics programming. I mostly do C stuff, a bit more C++, but and usually like microcontroller stuff more so than PC. Yeah, at the moment I'm starting to look into Bluetooth, the Nordic chips, but yeah, what? That's about it, I guess.
Okay. One software engineer-ish kind of thing. Yeah. Okay. Right. Now I'm going to be doing a presentation about this system here, but maybe we'll start off. Anyone got any interesting projects to report, questions, problems that need solving in the electronics microcontroller area? We're not interested in your domestic problems.
What if they intersect? Not too much intersection in this meeting, please.
No? Everyone's happy? No problems? Yeah, John's got a problem.
Perhaps we should do the occasional, or perhaps every meeting reminder that these sessions are being webcast. Not webcast. Yeah,
Recorded and put on the web,
recorded. Yeah. I think it goes out live, doesn't it?
Do we go out live, Bill?
Yeah. So.
Doubt if anyone's watching, but hey, we're going out live. Yeah.
So just be aware of that, and we do record it. Anyway, there's an exhibition coming up called Electronics. Not electronics. Electronics ends in NEX, as in exhibition. So it's an exhibition in Jeff's Shed. They happen every 2 years in Melbourne, and alternate years are in Sydney. So 11th and 12th of September this year, so next month. I think you'll find, if it's anything like the previous one, it's not hard to get in free. In fact, by and large, it's generally free, and there are some pamphlets that Brian's brought along at the front, so help yourself to a pamphlet. Recommended. It is very much aimed at a fair bit of manufacturer side of things, so it's not so much the one-offs, but I think you'll find that it's worth looking around, and there'll be a lot of gear up there. That's probably all at the moment, but I might come back with a separate question about time references.
Well, do you want to do that now? If you go, we've got the expert here.
Yeah, okay.
Go for it.
This might be largely aimed at Max. One of our group on Saturday spoke to me about trying to get a time reference. Now, I'm wondering whether we ought to talk a bit about some of the simple circuits that are around. But he's got a GPS receiver that puts out 1 pulse per second. That 1 pulse per second is really, really accurately per second. You're talking like 10 to the minus 9 or 10 or something or other, something of that. Yeah, that sort of accuracy. He would love to have a way of frequency multiplying that up to 10 megahertz. And still maintain that sort of level of accuracy. Now, just as off the top of your head, a simple phase lock loop would probably jitter too much. Yeah.
Yeah, you need to be able to do that. To
be able to do that, you really need a micro, and they do counting from the 1 PPS. It's difficult to get to 10 megs, but it can be done, and they do it.
Yeah. Anyway, it's probably good for a few people who are interested in that. I'm a bit interested in that and not much experience, but Bernard's is the guy. Do you know Bernard's? He turns up here at times. He was here on Saturday. And John Macy's a bit interested in that sort of stuff, I think.
Yep.
Yeah. Has anyone here had much experience with phase lock loops? I have a bit, and I'm sort of keen to do some more. Does anyone know what a phase lock loop is?
Oh, yeah.
Anyone doesn't? Okay. Phase lock loops started their life in the analog world, but they're also applicable in the digital world. How do we do it? Call it a voltage control oscillator. So the frequency, voltage control frequency, and we have a phase difference circuit. So we have a reference signal coming in. It might be noisy, it might not. And we have this voltage controlled oscillator, and it is a more complex thing of a typical negative feedback system. So this is the minus input and this is the plus input. And so the idea is that the frequency and phase of this output tries to track the input. And so it's done by comparing, quite often there's implied frequency sensing as well. So when you're way off with frequency, the thing will actually detect the frequency is wrong and the difference and amplify it around the loop. And so change the voltage on this oscillator, changes frequency so that the frequencies match, and then it pulls in and actually matches the phases as well. Does that make sense? People who have had some amplifier type background. Now, one smart thing you can do with that is just to say, look, I really want to have a higher frequency coming out of this. And so if you put a digital divider here, if you divide it by 10, then this voltage here is going to be adjusting this oscillator so that it gets 10 times the frequency, and when this is divided by 10, it's the same as that. So what comes out of here is going to be 10 times the frequency of the input, and it's frequency locked to it. So if this is an accurate, and that's the whole point of this project, if it's accurate, really accurate, then you can get a signal out here that you hope is 10 times as fast, or 100 or 1,000 times as fast, and also as similar accuracy. So anyway, I've got a few chips at home. There's a fairly old chip now called a CD4046, which does that job. Actually, you have a filter in it here too. Sorry, I forgot the filter. A low-pass filter. Is that right? Yes.
Yep.
Yep. So it measures the phase difference and it smooths out the ripples, and so you get a fairly constant DC voltage driving this voltage control oscillator, and it adjusts the frequency here such that the frequency here and here match. Yeah. Sometimes, if you're trying to do real precision work, you end up having to buy really expensive things that are in this space. I think that's about right, isn't it? Yeah. Max has got a fair bit of experience with it, yeah. So some of us might start fiddling around with these things. I'd like to have a go at these sorts of things too, and yeah.
They started off life in the analog world when the guys were looking at communications receivers that they wanted to be able to have an accurate frequency source and be able to tune it accurately.
Yeah. And so in that space, you'd have sine waves probably.
You'd have sine waves, that's right, and a reference crystal oscillator. Yes. But it became a tunable communications receiver. And it got away from the old-fashioned just LC tuning to something much more precision in setting frequency.
Yeah, I was surfing around the net over the weekend after this guy Bernard asked me about it, and I found a device in this space that looked like it was fairly expensive, and it was some thousands of dollars, I think. And it's, it was a crystal oscillator with voltage control on it, and I think you could change it by something like 150 parts per million only, up and down. So something like that, and a stable one, would probably mean that the jitter, that you want it so that these edges are really precise, and if you've got a little bit of noise and rubbish in there, so that this edge will jitter backwards and forwards. That's a bad thing, and you want to reduce that if you're doing precision work. Yeah. Anyway, that's probably enough about that, but some of us are a bit interested in that sort of stuff.
And if you, with that that circuit there, if the divider, I guess you have a divider in there somewhere,
yes,
for multiplying.
There was a divider.
If you can dial up the division ratio, you wind up with something called a frequency synthesizer,
Yes.
where you can set. It gets a little more complicated than that when you're going over a wide range of frequencies, but that's
yes,
the basic idea. Yeah. You can actually make a voltage-controlled crystal oscillator quite simply with a variac diode.
Yes.
Max will give you a circuit.
From one part pulse per second, it's difficult.
Oh, to get that multiplication factor, yeah.
The multiplication factor is
Yep.
huge.
Yeah.
One way of doing it is counting pulses over 10 seconds,
Yep.
and then counting the other pulses,
Yep.
and comparing if there's too many pulses, it'll drop the voltage.
Then have a D2A that's controlling a voltage
blocks it
controlled.
that way.
Yep. Yep.
The other way, there's another circuit around. One of the GPSs has a 10 kilohertz output.
Yeah.
That you can multiply up quite
More
nicely
readily, yeah.
to 10 megs.
Yep.
Well, actually,
And,
I did sort of summarise it a bit.
Yeah,
Bernard
but
told me...
the voltage-controlled crystal oscillators, there's a whole range of subgroups in that. The acknowledged really good one is the Hewlett-Packard.
Was it a double oven thing?
There's double oven ones,
Yeah, I saw someone talk about that, yeah.
but single oven ones in a box that's not quite fully insulated is good.
Yeah.
Yeah,
Anyway,
but they're about sort of, the oscillators are second hand, about $50.
Oh, okay. Yeah, this guy picked up a time reference that was being thrown out from Telstra from an exchange, and so that's what he's got here.
Yes.
And so that's what he's thinking about as a starting point. And the other thing that is along the lines of what you're saying is he tells me that his GPS receiver has an option of somehow changing it so it can have a 1 kilohertz. I think he said 1 kilohertz output.
You can, some of the
yeah.
boxes,
So that's an improvement.
You can cause it to give an output frequency from 1 to 20 megs.
Yeah.
1 pulse per second to 20 megs.
We have two extremists in our group. Bern's one of them, and Max is another one. Max has an extreme time reference laboratory at his home. Anyway, I think we probably ought to move on. But
I
yeah.
think it's called
Yeah.
a frequency fetish.
Yeah, I got bitten by the bug long ago, and I have let's see, 1, 2, 3, 4, 5 GPSs, 3 currently running quartz oscillators. About 2 months ago, I had to pull the plug on them, and that killed them.
Yeah.
These quartz oscillators have to be kept running all the time.
Okay.
There's one in my
Don't you have
frequency
something a bit
count.
fancier? Haven't you got an atomic standard?
Yes, I've got a rubidium standard, and I've got 2 more to be completed. I've
That's
got
not
my
fetish, that's
comparison
terrorist.
Pardon me?
I said that's not fetish,
Yes.
that's terrorist.
Yeah, well,
Okay.
I do. My problem is I acquired a frequency difference meter, which lets me read to
Oh dear.
something like easily subparts of 10 to the minus 11 to compare 2 frequencies. So I'm deep in the noise of my GPS, and I want to build a phase lock loop like that with the crystal oscillator on the output with the division of 1. So I put 10 megs in as a reference, and I'll get a nice 10 megs out without all the noise. So I'm real keen to have a go at this.
Okay, well, we're talking about frequency and time. I promised to show you how I made time stand still, well, nearly. Back in the 1969th year of the Christian era, circa. I can't remember exact year. But the thing was around this plant here, which is the Alcoa Alumina Refinery in Kwinana in Western Australia. You may recall 4 years ago now, a mate of mine from Perth came over, Bruce Varley, and gave us a talk about PID control loops. Do you remember that? Bruce and I actually met here on this particular project back in '69. And I had to contact Bruce yesterday to ask him a couple of details about it, and I'm afraid he remembered better than I did. So in these plants, you can see there's an awful lot of these round structures here. I couldn't tell you which is which, and this whole thing I'm sort of working from a memory from literally 50 years ago. So I won't get all the details right. But there are an awful lot of tanks there in that plant. Somehow or other, and I don't fully understand the process, they get this bauxite, aluminium ore, and they use caustic soda to dissolve it and leach somehow the alumina, which is probably aluminium oxide, out of it, and then separate the chaff, all the rubbish, from that. And I guess it's the liquor that's the good stuff, and the rubbish goes out. And they have a lot of these settling tanks. And they're structures, probably, you could, not too much of a stretch to say a circle just fitted inside this room with roughly that sort of height and roughly this sort of diameter. You go out and you walk across these things. You hope it doesn't give way, because if it does, you're going to plunge down into hot caustic soda, and you won't last very long. And while we were walking around there, Bruce kept on regaling me with stories of people who'd fallen through the hatch and what have you. And there wasn't much to pull out after 5 minutes.
What they used to say is if someone goes in, the best thing you can do is push them under.
Yes, yeah. Oh, you've had some association with that.
I worked for Alcoa for lots of years.
Oh, okay. Well, you know more of the process than I do then. Yeah. Do you remember, were you in Kwinana around about that time? Chief engineer was Irv something or other, American? No. So, now these settling tanks, they have a big paddle that goes around. Slowly, it takes probably several minutes to go around. But the challenge for the little company I worked for, which was called Precision Electronics in A Street Subiaco was to find a way of monitoring the level of the mud as it settles down in the tank. And that apparently was quite an important thing for the process people to know. And they needed it to come out on a chart. So this doesn't show very well, but it's sort of almost like a radar, and it's dark where the mud is and so on. And I'll just sort of jumping forward a bit, in the final thing you could actually see the paddle coming around as well. And we decided to do that using an ultrasonic fish finder. Quite literally bought a Ferrona fish finder, pulled the electronics out of the thing, took the transducer, which was a sort of a brass thing about yay fish-shaped to slide through the water on the bottom of your boat, and used the electronic guts of the thing, but we had to discard everything else. Now, with the fish finder, the range, of course, is fathoms, not feet. These tanks are only a few feet deep. And the total echo time for these tanks was about 8 milliseconds. Now, in the Ferrona fish finder at the time, what they had a rotating needle, arm on a motor, and a neon light. And synchronized with the pulses of ultrasonics, and the signal coming back, the light would flash. And so you could see where the fish were in this sort of rotating gizmo. These days, of course, they have liquid crystal displays and all good stuff. In those days, it was this rotating, flashing light. But Alcoa wanted to have a system where they had a permanent record, hence the chart recorder. Now, you can't replicate an 8 millisecond echo on a chart record that's going to take preferably several seconds to go across. And so we had to find a way of slowing that signal down. Now, these days, you'd get a high-speed A to D to A converter, squirt it into memory, and then plot it out slowly out the other end. But we couldn't do that in those days. We just didn't have that sort of digital technology. So what I did, and this was actually the first serious project I ever did in my career. So I came up with the idea. I'd learnt about something called a sampling oscilloscope. Who's heard of a sampling oscilloscope before? Okay, who can explain how it works? Oh, it's left to me then. Okay, so imagine you want to build an oscilloscope that can replicate frequencies in the gigahertz, really, really high frequencies, onto a CRT, onto a cathode ray tube. And that becomes very, very difficult. But if I've got a repeated waveform, like that, if I was to just do that straight, make an oscilloscope to go straight in that, I'll say 2 cycles. I want to show 2 cycles on the screen of an oscilloscope. I would have a time base that looks like that, driving the horizontal deflection of the tube on the tube. Preferably they're all going to be equal, but the way I'm drawing it, they're not. That would be the time base. Now, you just can't build the electronics, or you could not in those days, build the electronics that was capable of, in real time, getting that waveform onto the screen. All the vertical amplifiers would have had to have a bandwidth of megahertz, of gigahertz, just wasn't on. So what you do, this is where you slow down time. You have that time base, which is the signal time base, and then you make another time base, which drives the horizontal deflection that looks like that. There's the 0. So it goes much, much slower than the real signal. But then what you do is, actually, no, I have to draw that on there with a failing pen. What you do is each time those 2 cross over each other, you sample the signal. I missed one. Yeah, I've drawn it so badly, it's really, really hard to see. Not very convincing at the moment, is it? Well, the signal I've got to send through to the, I should be, I probably should draw it with a lot more low frequency ones. I'm probably running into Nyquist limit there, don't you think, Max? Probably.
A whiteboard Nyquist limit.
A whiteboard Nyquist limit, that's the one. Yeah. Yeah, I probably should have a lot more cycles in the whole thing. I'm trying to draw it with just 4. But effectively what I'm doing, I'm sampling. Well, the first thing I can do is to have 1 sweep per cycle. That'll make it a little better. I told you I was going to wing this, didn't I? Have I got that right? Something like that. And the other one goes... that wasn't too bad. So I'm going to sample there, I'm going to sample there, I'm going to sample there, I'm going to sample there on the downslope, I'm going to sample there. So now it doesn't look too convincing either, but I've more or less reconstructed that shape, but much more slowly. Can everyone kind of see that, despite my beautiful artwork? So that's how a sampling oscilloscope works. This is all typically done in analog domain and an oscilloscope, so you've got 2 time-based, literally oscillators. This one has to be fast, but that's not too difficult, even in analog, to make that. But once you've got that, and the trick then is that when you've got that signal, you actually hold it on the display until the next sample. Like that. So there's a sample and hold circuit. That's a circuit that can grab a voltage and hold it over a period of time. And with a bit of Tektronix or Hewlett-Packard type circuit through magic, you can get an oscilloscope that will display gigahertz repeated. They have to be repeated signals. You can't get a single shot transient capture with that. But for the RF kind of guys, that's pretty okay. By doing that, they only need to have a little bit of very high-speed circuitry, maybe the very front-end preamplifier. The sampling gate is usually done with a diode of some sort.
Quad diode.
Quad diode, okay, a little diode bridge and a capacitor and stuff like that, yeah, yeah. And as I said, a little bit of Hewlett-Packard.
Blows up regularly.
Right, if you overload it.
Second-hand sampling scopes.
Yeah, they're usually blown. Yeah, yeah, yeah. And I said a little bit of Tektronix or Hewlett-Packard magic, because the guys that develop these things, I mean, they know their stuff analog-wise. It's just quite awesome what they can do. So the challenge, so I decided I was going to emulate that, but I was going to do it digitally, make that time base digitally. Because we were just in 1969 of Christian era, we're just beginning to get reasonable medium-scale integrated circuits at an affordable price, which was sub $20 or maybe even sub $10 for a 4-bit counter chip. So that is what I cooked up. So we were going to ping the ultrasonic, the fish finder itself, at a rate that's sort of commensurate with 8 milliseconds. I forget the detail. I think it was probably every 32 milliseconds, so it'd be ping, pause, ping, pause, ping, pause. And we made a digital, or I designed a digital time base that used 7493. There's no LS or any of that fancy stuff, or CMOS or anything like that. This was the full-on, it's going to burn some power type TTL chips. counters. You see on that screen there, we've got the 7493. This data sheet post-dates this time era because we only had 7493s. We didn't have any other fancy stuff. Is a 4-bit binary counter. Does anyone not know what a 4-bit binary counter means? Everyone knows that. Good. For you software people, it's something that can count from 0 to Fox. Okay. So we got 2 of those. And we put a clock into there. I have no idea now how that clock was generated. It's fairly unimportant. A program will be JT or something like that. And of course I had to have 4 of them, not 2 of them. Now if we arrange it so that, well, I think I use 7 bits per section. So if we arrange it so that that bit there, the 7th bit, this is the least significant, that's the most significant. If that's there is about 8 milliseconds, we wind up with this one, I forget the exact number, up here being 512 times 8, which is 4 seconds or something like that. Seconds, doesn't matter. I think it was 8 seconds or something like that. I did the sum before I came out, but I've forgotten. But now we're down to a speed here which is consistent with an electromechanical chart recorder. You can have the thing sweeping back and forwards in 8 seconds. I forget it was 4 or 8 seconds that we did. So now I take those 7 bits, because I'm going to use 128 steps in my sampling, and I take the top 7 bits and I put them through a couple of 7485 binary comparators, numeric comparators. And that has 3 outputs. It has equals, it has less than, and it has greater than outputs. Can you see where this is headed? So I'll show you that. 7485 4-bit comparator. Again, didn't have any LSs or anything in those days. I think we maybe had 74L. I did use that around this era for something. So now we have a signal out here, the equal signal, which is going to go off where the high frequency count intersects the low frequency count, where the 2 sawtooths intersect. Do you get that? You're not going to be examined on this, but nice if you kind of grasp the idea. So now we've got a digital time base, we've got something to work with. That then needs to go into some sort of circuit that's going to sample the analog signal and present it to the chart recorder until the next sample pip comes along. So it's the output of this sampling thing is going to be some sort of staircase signal.
So when that equals pulse goes high,
yep.
It's grab the analog signal
yep.
and hold it
until the next 8 or 32 milliseconds or whatever it is there, yeah. Okay. Exactly. And we have time slowed down, okay. Nearly standing still. Yeah. So that I'm sorry? Oh, come on, admit what? Come on.
I said, how come you put grey hair?
Oh, I had long locks back in those days, and I wore flared pants and the whole thing, and had my slide rule in my top pocket, and I was a very cool engineer. You don't know what a slide rule is, but don't worry about it. Early computing device. Didn't need batteries, no, and you could whack people with it if you really needed to. And I think I got my first calculator, electronic calculator, in 1971, 2 or 3 years after this thing. I had went to Singapore for our honeymoon, and the calculators were dirt cheap there. It was only $125 for a 4-function calculator with a memory. It was really, that was something. It was fantastic. A little sharp calculator. And I learned how to do square roots on it using a Newton-Raphson approximation. My finger was practiced, trained to do that square root thing. So that's one part of the overall equation of this system. Now, of course, we've got a chart recorder. What I haven't mentioned yet is this chart recorder was picked specifically because it uses electrosensitive paper. So it has a... Pardon? No, there's more than that, Max. More than no ink to dry out. Because this is the one there. As the thing scans across, the actual stylus is a little gold ball, sort of hemisphere. As it scans across, the amount of... And we actually just borrowed one from Hewlett Packard, said let's give this a try. The darkness of the line depends on the voltage you apply to it. So you can actually modulate the trace. Aha. Exactement, monsieur. That was the key. That was one of the keys to the whole thing. So we could, so that's why we could get a trace that's sort of nothing, 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 coming darker, darker, like that. Got that Z modulation on that display. And you add lots and lots of lines of those, and you start to build up a picture.
Now I know why you say that particular model, that style of chart recorder, did traverse fairly slowly, whereas the ink ones could scream across the screen.
Yes, I can't remember the numbers. I don't remember the numbers, but we didn't have to stress it too much. I'll get back to that in my emails with Bruce today, actually. So the sampled signal, it's been sampled from the sampling time base, that's slowing down time base, gets fed to an amplifier that, I think it was only 30 volts, so that was fairly simple to make an amplifier that go 0 to 30 volts from that signal. And it would have been the envelope of the 40 kilohertz ultrasonic signal, full wave rectified somehow. Forget the details. Maybe he didn't even bother. Maybe he just fed it straight in. I just can't remember. So that's the other element of the puzzle, is the electrosensitive paper on that chart recorder. Right, but we've got to get that thing to go across. Got to get it go across and then whiz back. Go across, whiz back. Now that whiz back time is also part of the reason for having a few bits between there. So there's a reset time, which is actually 4 times or 3 times 8 milliseconds. So it got back. And in practical terms, it wouldn't really matter if there was a little bit of not quite linear there, because it's still going to give a readout that is useful to the process guys, and that's really what matters. So the next thing is that there's the comparators. We also take this signal, which is a binary representation of what we want the chart recorder to do, and we put it through a D to A converter. I'm not sure you draw one of those. A D to A converter, digital to analog converter, to become the I'm going to say 0 to 5 volts, I can't remember, 0 to 5 volt signal, just to drive the chart recorder backwards and forwards, or like that. So you couldn't go into Dick Smith in 1969 and buy a digital to analog converter. I actually had to design one from scratch. We didn't have CMOS chips. So how do you design a digital to analog converter when you haven't got precision switches, analog switches? You just try to get cunning about it. So from memory, and this is only from memory, what I did. Sorry? No, FETs didn't. We didn't have FETs. No. Not that I had access to, and you'd have to have high side FETs anyhow, which would get, sorry? Really expensive. So I found this little NPN silicon transistor from RCA, which I thought was the bee's knees, which had 100 millivolt saturation voltage, max, at some reasonable current. And I thought that's really important. I can't remember what rail voltage I ran the whole thing at. I'm going to guess 10 volts. So I used an R2R network where you have I won't draw 8 or 7 bits worth of it. So that's R, 2R, 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 and 2. I think I'm a little uncertain about that. 2R, and each of those can be switched either between 10 volts, whatever you're going to use, whatever the voltage is you're going to use, the reference voltage. Like that, or ground. And those of you who are mathematically inclined can prove that the voltage that comes out there is equal to that divided by full scale number of bits times the binary number dialed into those switches. If they're dialed in for 0, this is what I mean, 4 bits, so if I've got 0 there, I'll have 10 volts, near 0 volts. If I've got Fox in there, all on, I'm going to get actually 15/16 of 10 volts. You will never actually get to there. But that's okay. So there were 2 aspects to this. I couldn't even go to Dick Smith and buy an R2R network. So I had a problem there too. And we're talking about Perth, Western Australia. In Perth at that time, a mate of mine around about that time had set out to drive his car to Kalgoorlie. He hit a lamppost, he survived. He took down the telephone line between Perth and the eastern states for the next 3 days. That's what communication was like. If you wanted to order something, you would use the telex, you would not use the phone, because the phone call to Melbourne to order something from Warburton Frankie was a long distance call, and that was, operator, can you please place a call to these people? Beep, beep, your 3 minutes is up, do you want to extend? Remember those days? You don't. And so, Perth is the most remote capital city in the world. And in 1969, when you're working there in engineering, it's bloody remote. It's like, we make do with what we can do. We had a local store called Atkins Carlisle who did sell some electronic components. And that was it. Half my job was actually running down there on my bicycle to pick up 3 resistors or something like that. It's so different to today. So the R2R network is one issue for this thingy. And the switches are another issue. I forget what I did for an op-amp. This was in the era of the 709. $5 will buy you an op-amp that's a load of whatnot compared to what we get today for 5 cents. Almost literally. That's $1969, by the way, which is more than a week's wages for me. No, that's not true. I was earning $44 a week. Nearly a day's wages for one op-amp. That's how it went. So the R2R network will solve that one first. So we had one beautiful, beautiful instrument in our company, which was a Solartron dual slope integrating digital voltmeter. replete with Nixie tubes and a Western standard cell reference inside. This was a seriously good piece of kit. I'm not sure how we got to have it, but we had it. So, and we had access to any number of resistors of the same value, but they were carbon film resistors. Carbon film resistors, huge temperature coefficients, 5% tolerance there, you know, not pretty good. And for a 7-bit converter, you need about a 1% or better tolerance to be able to hit the mark. So what I did, literally, I got a whole pile of these resistors and put little paper labels on them all. I soldered them together in a string, long string. Let me see. Oh, now this was going to be 2 resistors in series, of course. 2 10Ks in series, or whatever the value I used. I think it was 10K. So I got that's 3 per bit times 7 bits is about 21. I've got probably about 30 of these resistors. Sold them all together on the bench, lying out on the bench. Put a voltage across them. Then I went over with this beautiful voltmeter, perfect digital differential input on the thing, measured the voltage across each one and noted it down. Then I sorted them on a piece of paper according to their values, because now I've got the relative values of each of these resistors. I sorted them. Just imagine that this is the things sorted. For the most significant bit, which is that one, I took those 3. So they're as closely matched as you're going to get. And then I sort of progressively assigned them to less and less critical bits, but going from each end so that the floor in the too large value of one is offset by the too small value of the other. And so I had this completely hand-picked and matched, thank you, set of resistors that went into the board. Quite literally. So that was that problem. And this worked. There was never any sign of this thing sort of going like that across the chart. It was one smooth transition. So that was that. For the switches, I quite honestly can't fully remember what I did, but I think, and this would be where a bit of a flaw lies, I think I used these transistors. 100 millivolt saturation in the on state, a pull-up resistor, and a diode like that to a reference rail. And that was the switch output. And out to the 2R network there. So on state it's switching almost perfectly ground, and 100 millivolts or less. Was it 100 millivolts? Might have been less than that, 50 millivolts or something. In 10 volts is nothing. No. They cost extra money. They're more than the sort of regular run-of-the-mill transistors, BC547, BC108s that we used, or 2N3704s. No. We're in the silicon era. We are in the silicon era. Yes. Yeah. They were about $1 each. Yeah. They were about $1 each at that stage. Yep. So, $1, 2 cents or something now. The only thing would be the matching of those diodes, and I honestly can't remember. In fact, I can't remember that was what I did, but it would seem to have been the logical thing to do. Because to have pull-up high-side drivers would have been almost unthinkable cost-wise. Almost unthinkable. I could possibly, just thinking about it now, another way to consider that would probably be something like this. No, I can't. No, I won't do that. I'm not sure. I'd have to sketch it up a few times. So, but when this D A to D was, or D to A converter was a whole board. You can see on the it was a 19-inch rack unit with boards that high. They were big boards, and the digital analog converter was a whole board on its own. It was silly stuff. By modern, one little pick and you're done. So that was the D2A converter, and that seemed to work pretty well. I'm not sure what would happen if we got an order for 50 of these systems, because that would be an awful lot of resistor sorting to do. So, any questions about that section? I'll move on. Also consult my notes. Right, the final bit of skullduggery was at the other end. Now basically this chart recorder and all the electronics were sitting in a control room. The tank was get on a push bike to get their distance away. So it seemed that, and this was getting into an area that I was not very knowledgeable about. Max would know more about it because it involved coaxial cable and all this sort of stuff. But I concluded that we would need to use a coax cable to bring the signal from the fish finder back into the control room to be displayed. So we'd ripped the guts out of the fish finder, the printed circuit board, must have made a separate board to go with it to match it, and it was sort of in a big sort of industrial type box with a key and stuff there. Bruce and I, we worked on this thing, commissioning it. We had to work in the evenings after the unionists had gone home. Otherwise, quite literally, we're not. If I had been caught holding a screwdriver on site, I would have been banished. I would have been. Pardon? There you go. I would have been banished. Bruce would probably. God knows what would happen to him. So we sort of met at 5 o'clock in the evening. I remember the drive down there. I had an old. Not so old actually, Fiat 125 at the time, driving down through there, and between Fremantle and Kwinana was a leather tannery. It didn't matter how much I closed the windows and shut off the vents. That's, I can almost smell it still. It was awful. Absolutely disgusting. So, and then we used to sit in the pub and go, after finish off, and go and have a beer in the local pub. So, what was I going to say? So we had the fish finder type kit mounted on a big steel box right there on the tank, and somebody had run a coaxial cable back to the control. I can't remember the detail. I suspect that I must have used some sort of signalling outbound from the control room to trigger the pulses, because there was nothing done in that box, I'm sure. So maybe I had a sort of a DC on top of the AC signal or something like that, an oscillating inductor or something. I just honestly can't remember what I did. But we only had a coax run, I'm pretty sure of that. So I wanted to, I've got this fish finder. Not sure I draw a symbol for the transducer. That comes through some Ferrono gubbins here. What comes out here is a signal that's looking something like that at 40 kilohertz carrier with the echoes on it. Want to get that several hundred meters back to the control room with reasonable signal integrity. So I was literally ignorant of such matters, so I decided two things. One, I'm going to boost that signal up as big as I can make it. Let's talk 10 or 15 volts here. Let's not ponce around with 200 millivolts, let's have some serious bit of drive there. And I'm going to impedance match it. So I've actually got an amplifier with a 50 ohm output impedance. And I remember what I did, I didn't want to do amplifier, and out. I didn't want to do that, because if you have a zero impedance amplifier, a series 50 ohm resistor, and then you're going to lose half your voltage. I didn't want to do that. So I have to admit, this one I scouted around for and I found the solution, and it was actually an amplifier with an actively set output impedance. And how that works, I confess I had to actually go and re-Google this the other day to remember how I'd done it. So, you got it. Assuming this is an op-amp type thing, I actually found an audio amplifier with a sufficient bandwidth, sort of a early days audio power amplifier type chip that would give sort of 10 volts or something more peak to peak, I forget the numbers. But it could be treated as an op-amp. So, I'm just going to say 1K, no, make that 10K, 1K, like that. Now if I connect that to a load, like that, as long as the amplifier is happy with the situation, I'm going to have a 0 ohm output impedance. If I've got 1 volt there, I'm going to have 10 volts there, and that's going to see 10 volts. Now, given this is 50 ohms, which is my coax, when I connect that, I want that 10 volts to drop to 5 volts. So what I do is I have a second feedback path. Oops, not like that. I have a second feedback path. A little bit of sleight of hand here. That's basically as a sense resistor. So when I connect the load, the current through the sense resistor, fed back through that resistor, halves the gain of the amplifier. So now I've got the situation where when the load is connected, the output voltage drops by half. I won't put the numbers in there because I'll get it wrong. But it's not, that's an exercise for the audience. So, oh, but I hear Max say, you've lifted your load off ground, which is not good. The load is no longer grounded. But the solution to that is this. It's a transformer. Now you know why I drew that as a block. It's a transformer. And in those days we went backward with sort of getting ourselves a P18 pot core and winding little transformers and stuff. Roger.
So where's your transmission line? Is that on the back end of the transformer?
Yes, yes. That I'm just the line. This then goes out to the like that, and we've broken any potential earth loops at the same time. So even if we hadn't had this scheme here, we would have used a transformer just because we're talking about two sites that are hundreds of meters apart, and the earth potential differences. I've had enough potential difference between two power points to blow up the output of a Centronics printer interface once. So you don't do that on an industrial plant. You make sure there's no earth loops. We possibly even had a transformer at the other end. I can't remember anymore. And so that was how we got a controlled impedance drive for that line. And I think the trigger signals must have come back down the line. I've really forgotten. We might have an inductor here and feeding through. Sorry? Yeah, some scheme. I can't remember.
There could be center tap on the
yeah. 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 Honestly, cannot remember. And it would have been whatever young lad could dream up as well, because this was my first serious project. So that was the tulips system. Unfortunately, we only ever made one system, and the system, basically it failed, and it failed for two reasons. One was we could not get the transducers to survive that environment. It's nasty, 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 nasty. That was sort of something, and I'm not blaming him at all, but that's kind of a thing that was left to Bruce to try and sort out. What can you do to have this ultrasonic transducer in hot caustic liquor not vanish within a short period of time? And I also learned from Bruce, just with the correspondence today, that the other problem was that we were actually hitting that chart recorder too quickly, too hard. So it was designed to just draw a line down the middle of the paper, and we were sweeping it back and forwards every few seconds. And literally the wire to the print head, to the stylus, was breaking off. That's it. So we were using it beyond what it was really designed for. And that became a bit too hard. So apparently they went and engineered another system, and Bruce, despite the fact he hasn't worked for Alcoa for a long time, he's happily retired, will not and cannot tell me what they did, because he signed the NDAs, and he's loyal to those NDAs. He several times sort of over the years said, "Oh, I'm telling you this, but you can't tell anyone else." So yeah. So I don't know what they did, but apparently they had a bunch of really clever guys, and they came up with something which probably wasn't even ultrasonic, some other way of sensing it. So that's it. That's me. Yeah. I guess I know. Oh, thank you. How are we going for time? Got heaps of time, have we? Oh, should I slow that down a bit? Let's have a break.